physics applications of derivatives. We've talked about a little bit of this so far, but we hadn't really done too much with derivatives then. So, okay, to begin with, on this first page, I just want to introduce you to some terminology. Displacement, generally in physics, we use S to represent a displacement. And what that means is that's how you're displacing from the beginning. Okay, when you leave class today, you're going to displace, right? You're going to go somewhere. Okay, you can actually graph out your displacement, you know, on an XY axis if you want to. So that just means where you are in relationship to the beginning of your journey. Okay, so we usually call that a position function like this. And the main idea with this is what you're doing with this function f of t is you're just adding delta t. Just means at a certain increment of time you have moved to some different place, possibly, is all that's saying. Okay, so that is the letter that you want to see. Anytime you see S in physics, that's talking about your position. Okay, we've already learned about this stuff, so I'm just going to review this real quick. If you have a secant line, so if you're graphing out your displacement, see this graph in black, that is your displacement. And what that would mean is at some time t, that would be where your position is. So for instance, right here, at that point in time, this is really a time t, some specific time t, you have this function value. That's how far you are from the beginning. And if you're looking at a secant line, you're looking at average velocity. So when you're doing average velocity, you're comparing the velocities of 2 points in time and finding their slope, basically. And then instantaneous velocity was more the slope of a tangent line. So whereas this is a slope of a tangent line, like we learned, a secant is just a slope between 2 points. You have 2 points on the line like that. Okay? And then what you're doing is, we've already been kind of working on the derivative, so the velocity is going to be the rate of change of the position, so it's going to be the position, it's going to be the derivative of that position function, okay, is what you're going to be getting. So a couple of simple definitions, and then we'll go to the next page and kind of learn the concepts of what these are doing, is average velocity. This is not new to you. That's a difference quotient, right? That is a difference quotient. What you're doing is you're finding a slope of a secant line with 2 points that are on that graph. But the instantaneous velocity, what's the difference? You take this difference quotient, you take the limit as the delta time goes to 0, and what that does is that gives you a slope of a tangent line. Okay, all we're doing when we let t get close to 0 is we're making the 2 points on the graph become infinitesimally close. Do you guys remember that? You already did that a little bit on your test, that first test. If I had you do a average velocity or an average rate of change, you just use the slope of 2 points. Instantaneous, you're doing 2 points that are very close to each other. In fact, infinitely close to each other. Okay? So let's see. You'll kind of get this down a little bit as we do examples. So let's go ahead and work a little bit on this next page here. And this is kind of a nice problem that I took out of the book that kind of shows you how you could look at displacement. This is like a trip in the airport. So first of all, let me kind of look at this graph and let's make sense of what's going on in this graph. Okay, basically what's happening, I think if you read the problem, it says you start at 6 a.m. So there's a couple of little notes that you want to maybe write to yourself that'll help you a little bit. Okay, this is 6 a.m. You're on the plane. Okay, that's time is equal to 0. That's the beginning of your journey. Okay, notice that your function value is 0. So we would say f of 0 is equal to 0. What does that mean? It probably means you're at the airport and you're on the plane, and the plane hasn't started going yet. Okay, it's just getting ready to taxi and take off and everything. Okay, what happens is now when you get to the next hour will be like 7 a.m. Okay, well, what do you have? You have f of 1 hour is about, that's pretty close to what? 200 miles, okay? That means that at 7 a.m. you are 200 miles from the beginning, like that. and so forth. Eventually what happens here, when you get to like 3 hours, 3 hours would be like 9 a.m., then you're there. So that's about what, 14, maybe like about, you're about 1,500 miles from your journey like that, right? Okay, everybody with me on what that means? Okay, now what's happening is this. Okay, right here, if you go to 10 a.m., so right there would be 10 a.m., how far are you from your original starting point?
You're still at the same place.
Okay, so what do you think happened? You probably stopped, right? Okay, yeah, okay, for a while. It looks like from here to here, you had to have stopped, right? Okay, now what's happening is this. If you make it all the way out to here, like this is 9 hours later from 6 a.m., then you're back to pretty much to zero like that. So what does that mean? It just means that you're back to where you began. So if you look at that graph, what I get out of that is you're at the airport, then you're in flight. Eventually you land, right? Okay, and you're not going anywhere because the distance from the start's the same. But then what happens is you're going back to the airport, and eventually you get to a displacement of 0. So these function values are the displacements. That's at the beginning, you're 200 from the airport, 15 from the airport, and so forth like that. So tell me if that makes sense. That is like a way that you could graph a displacement like for an airplane trip, a round trip. That's how that would go. So what we're going to do on this is we're going to do some calculations on this. So the first question on here is we're going to calculate the average velocity during the first 1.5 hours of the trip. So from 0 to 1.5. Now this is something we've already learned how to do. So what we do is we need to come up with our 2 points. So I'm going to just kind of write down in this part A what those 2 points are. Okay, some of these things I'm going to erase. So I'm going to kind of start over again here with this. So we're going to do the first 1.5 hours of the trip. Okay, so we're going to go from that point to this point right here. So we need to just get those 2 points on the graph, and let's see what I used. I used 0, 0 there, and then this point is going to be a time of 1.5 hours. That's like 600 there, so let's say, what do you think, 500 approximately, or maybe 600. I'm off maybe a little bit on that. I think let's go to 600. Okay, I like that a little better. Okay, so what you're actually doing when you find the average velocity is you're really just finding the rate of change, or you're finding the slope of that secant line, like that. Okay, that's what this formula is saying, is it's saying, okay, what's S of A? Okay, so what you're going to have on this is really, this is saying this. Okay, it's saying that when you do the slope, you're going to do the 600 minus the 0 all over the 1.5 minus 0 like this. And this part right here in this formula, all that's saying is what is the distance between that last point and then the beginning. So 600 miles to 0. The delta t is saying what's the change in time. So that's 1.5 hours like that. So what that would give you is that would give you 600 over 1.5. If you work that on the calculator, you're going to get 400, I think that's miles per hour like that. So that is the average velocity from that point in time. Okay, like that. Okay, does that make sense to everybody? Okay, it's not hard, it's just doing a slope like we've learned. Okay, now let's see what this second question is. So the next question is from 1:30 to 2:30. So if you count it out, remember this problem said 6 a.m. there. Okay, so 1:30, if you just keep counting, that's 7, 8, 9, 10, 11, 12, that's noon right there. Okay, so 1:30 is here. Okay, and then 2:30 looks like right there. So the 2 points we're going to look at are going to be at 7.5. Which probably is there. I'm going to just think, I think it's there. And then that must be the end of the journey like that. Okay, so when we get into these 2 points, it looks like this point at 7.5, that's going to be 7.5. And then that displacement to me looks like about 200. On my notes, I used 300. I don't know why. Do you think it's 300? I can't see very good. So sometimes when I see this screen like this, I can't see real good. Well, see, that's 200 right there. So I guess 7.5, what I thought of is maybe it's a little more accurate if I was up there. Does that look any better? Okay, I can't tell. All right, you guys are young and got better eyes than I do. So the next one I've got what, 8.5, and then I got 0 like that. Okay, so what I'm going to do on that is I'm going to find, again, the slope of the secant line for that average velocity like that. Okay, so that's real simple. What you're doing is the slope formula. You're doing the change in the y values, 300 minus 0. Then you're doing the change of the t values in the same order. It's real important that you do that subtraction in a consistent order. So 300 minus 0, be sure you do 7.5 minus 8.5. So that's 300 over negative 1. So that is negative 300 miles per hour. Okay, if you haven't studied physics before, this may surprise you. You can have negative velocities. Okay, why is it negative? Because you're changing direction, you're going back to the airport, right? So what you're going to have is when you're going to your destination, like from here to here, that's going to have positive velocity. And then when you're going from here to here, that's negative velocity because you're changing directions. Exactly. So velocity can be negative, okay? So the idea is that's how you would figure out those two average velocity. Everybody okay with that? Yeah. Okay. Now there's a couple of things that I want to kind of have you pay attention here on this. So the velocity is 0 at a couple of places on this journey. Okay, remember, all that a velocity is a slope of a tangent line to this function. So if you look at this, let me stand up so I can kind of show you what's going on these velocities here. Okay, right now, you have a positive velocity because the tangent line is positive, right? And it's getting steeper. What does that mean? Plane's going faster, plane's going faster. Now what's happening? It's going at a slower velocity. What's the plane doing? It's getting ready for landing, right? Then when it gets there, what's happening? Okay, you stop. You must have landed, okay? And then you landed. From there to there, you must be at the airport and the plane's not moving. And then what happens is the velocity becomes negative, right? Because it's a negative sloping tangent line. And then eventually you get back down to 0 like that, okay? So what's happening on that basically is this idea is the velocity. This is what I want you to write down. The velocity is 0 from this point to this point right there. So that looks like from 3 to 5 hours. Okay, so I'm going to say on that from 3 hours until 5 hours. And let's see, the time on that would be 6, 7, 8, 9. That would be what, 9 a.m. To 11 a.m. Okay, so from 9 to 11, I guess you're at the airport terminal. The plane's waiting for passengers and that kind of stuff. Okay, and that's when the plane is at the airport, we're going to assume. Okay, like that. So that's the idea with that. Okay, so let's do this very last problem. That'll be kind of a good place to stop here today. We're now going to do, this one is asking for the velocity at t equals 6. Like that. So this is going to be t equals 6 hours, really, is what this is. Okay, so what we need to do is we need to go back to our graph, and now we got to look at a tangent line if we're doing this. So if we're doing this, let's kind of carefully go up to our graph, and we're interested when t is 6. We're interested in finding the velocity right there. Now, is the velocity right there going to be negative or positive? Negative, because it's going downward. It's sloping downward. So let's kind of carefully draw in a tangent line here. We're going to have to just sort of estimate this like this. So I'm going to real carefully draw in a tangent line. I think this problem was kind of designed so you can find a couple of good points. Okay? So what I'm going to do on this is I really, since that's a tangent line, I need to figure out 2 good points that are on that line. So let's look at maybe that point, and let's look at that point. Those are 2 nice points. Okay, so if I can find the slope of that, that should be pretty much what the slope of the tangent line is. Probably not perfect, but pretty close. So let's write down what those points are. This point right here looks like it has a t value of 5, and it looks like its y value is 1600. Okay, and then this point right here looks like that's got a time of 7, and it looks like its displacement value is 600. So for estimation of that velocity, what we're going to do is we're just going to use those 2 points like that. When I did this out of class, I did something different, but it doesn't matter. That's just kind of what I see, is that looks like a good tangent line. Okay, so let's work with those 2 points, and those are, let's see, I'm going to write those down. We have 5, 1600, and let's see, this one is 7 and 600. Now see, we're doing a secant line, but we're using that to approximate the velocity. That's the idea. Okay, so does that make sense why I chose those points?
You can choose 1600 even though it's off the function.
Yeah, I just tried to get as close as I could. I mean, you could, there's not any one right answer on this. You're just kind of estimating anyway, finding 2 good points that seem to be on that tangent line. Okay, so let's go ahead and do this then. So then what we're going to do is just calculate the slope. So we're going to do 600 minus 1600. And then you got to do this in the same order, over 7 minus 5. So that looks like that's negative 1000 over negative 2. So that looks like that's 5, what, negative 2? I'm getting in a hurry here, so that's 2. So that looks like that's negative 500. Outside of class, I did different points, but I got the same thing. So that means that that velocity is going to be approximately negative 500 miles per hour. Okay, like that. So that's an approximation for the exact velocity of a plane, which is pretty typical. That's a plane that's pretty much going pretty much at full speed, maybe just beginning to slow down. And then the last thing is the velocity is negative as the plane is returning to the airport. Okay, so I think that's a real good problem to help students see how displacement relates to velocity. You guys get the gist of what's going on there? Okay, that's kind of stuff you look at in physics, so we'll take this a little further next time in class.